Welcome you all for today's water and wastewater treatment live session. And I am Saptarshi Bose here, a PMRF research scholar from IIT Madras. As usual, we will try to solve few numerical questions and also few conceptual or theoretical questions. And doing so, you will be prepared for your upcoming examination as well as other job examination or gate examination. So the first question for week 4 is a numerical type question. It is a common data question for question number 1 and 2. Please write down all the data from this question because this data will be required for the next question, that is question number 2. It is about a completely mixed activated sludge process and that is used to treat wastewater flow of 1 mld. You know what is mld? Having BOD concentration of 200 mg per liter. Biomass concentration inside the aeration tank is 2000 mg per liter. Now the concentration of net biomass leaving the system is 50 mg per liter, and you can assume that there is no waste activated sludge. So, and everything is recycled into the aeration tank. The aeration tank volume is given as 225 meter cube, and you have to calculate that what is the hydraulic retention time. If you remember the formula, use that formula. If you don't, please refer to the note. You can take the help of the note to recollect the formula, but I will suggest that before this live session, you should try to go through all the formulas or the formulae before coming here, before attending live session. As usual, you can use your chat section to write your answer. Yes, HRT. Yes, yes. Okay. Let me check. I think I have one audio problem. Okay. Hello, hello, hello. I think now I'm audible, right? Yeah, thank you, Ruchita, for your answer. 5.4 hour HRT. Okay, we'll go for the solution. Yes, you are correct. The answer is 5.4 hour. Congratulations for that. And thank you for sending this quick reply. So the HRT equals to, here I will tell for other student, HRT equals to, is a very simple question, the first one. That is nothing but volume divided by the flow rate multiplied by 24. We are converting it. That's why in hour we multiply to 24. So this is the volume. V stands for volume and Q stands for the flow rate. So V is the volume of the aeration tank. Q is the quantity of wastewater coming into the aeration tank, excluding the recycled sludge. We are not considering recycled sludge. Only the whatever is coming here. We are considering this is as Q and the volume is V. So V divided by Q will basically give you what is the hydraulic retention time, how much time the water which is coming here in this place is staying inside this volume. That is the main concept behind this HRT. So T equals to, just you have to put the values. It was 225. I guess it was 225 somewhere, yes, meter cube. And please check the conversion, like this is 1 mld, 1 multiplied by 10 to the power 6 liter, and I'm multiplying with 10 to the minus 3 to convert it liter from meter cube, and multiplied by 24 to make it day from hour, and we are getting as 5.4 hour. I hope this is clear for everyone. So I will move to the next question. The next question, common data question. It is about what is the average time for which the biomass stays in the system. Average time for which biomass stays in the system. I hope you know what is the term for this and you can refer to this data.
Sir, question number two is asking for average time for which the biomass stays in the system. Is it SRT, solid retention time?
Yes, right.
Okay. Okay.
One more minute. After that, I'll go for the solution. Because today we have many questions to solve. Okay. So the solution correct answer will be 9 days. This is basically SRT, solid resolution time. How we are calculating theta c equals to v into x, whatever is inside this tank and what is going out. Basically, that ratio we are taking care of. Some part is going out as it will, some part might be as recycled, something like that. So the basic concept is whatever is inside that solid divided by whatever is going out, right? And this will give you the solid resolution time or the average time for which the biomass stays in the system. Basically, that's what we are taking care of. So here Vx, V is the volume and X is the what is the MLSS inside this tank, what is the biomass concentration inside this tank, and then this is the how much is going as effluent. This is if this Q is the flow here, then Q minus W. Suppose QW is going for the waste, right? Here you can see it was written as there no waste activated sludge. But suppose something is going to be wasted, then what will happen? Something is going to be wasted, that is QW, suppose. Uh, so here you can see, suppose QW is going to be wasted or recycled, whatever it is. It might be recycled or it might be wasted. And then this is nothing but Q minus QW multiplied by XC. So the concentration of biomass in the wasted sludge is XR or recycled, it depends. And this is the flow rate QW, is the flow rate. This is the concentration of the biomass. Again, the concentration of the effluent biomass, that is XC, effluent biomass, right? And this is Q minus QW. So this Q is going to be divided into two parts. One is Q minus QW, another is QW. That's the basic concept. So these part are going to be wasted or going out, basically leaving the system. Don't think about the waste, just leaving the system. And whatever is inside. So we are doing that ratio only. So this is 2000. In case it was given at 2000, yes, mg per liter, and then multiplied by 225 and multiplied by 10 to the power 6, right? So that was the volume. I guess what was it? Sorry, let me check. Yes, 225 meter cube. And that is, please check this one. I think this will be 10 to the power 3. Please check the calculation because I'm not sure about it. And then basically this is your concentration X and this is the volume. You may need to convert it from meter cube to liter or liter to meter cube, and then this is 0, right? So if QW is 0, there is no wasted sludge, QW is 0, then this term will be 0, right? This totally cancel out. This is 0, so it will be Q multiplied by XC at the bottom, right? At the denominator, it is Q multiplied by XC. This is Vx SRT equals to Vx divided by Q multiplied by Xc. Why? Because in our case, in this situation, QW is 0. We are considering QW as 0. So you just have to multiply it with this. It was how much? 1 mld was coming, right? Yes, 1 mld was coming, and another thing I had. Yes, this is 1 multiplied by 10 to the power 6 to convert it from mld to liter per day. That's why I'm multiplying with 10 to the power 6. And then this Xc, how much it was? It was around, yes, 50 mg per liter. So the net biomass leaving from the system is 50 mg per liter. So this Xc was 50. So this Xc was 50. Right? So that's why I'm writing 50 and I'm getting as 9 hours. Please check the calculation. Might be might be some error during this conversion. So check carefully. Now the next question, again related to activated sludge system, is in equilibrium, and there are following information. Again, common data question. Flow rate 500 meter cube per hour. Influent BOD is 150 mg per liter. Effluent BOD is 10 mg per liter. Aeration tank related data is given as hydraulic retention time HRT 8 hours. Mean cell residence time as 240 hours. Volume as 4000 meter cube. Then MLSS as 2000 mg per liter. So this is the data. Please try to write down the data. I will again come back to the data sheet or this slide. So now I will proceed to the question. The F by M ratio, food to mass ratio you need to calculate. The unit is in kg BOD per biomass per day. So for the aeration tank you have to calculate. I'm again going back to the data slide. You need to calculate M by M ratio first. Okay, Ruchita, I got your answer. Thank you. We'll check. We'll wait for 1 or 2 minutes, then I will go for the solution. Uh, yes,
Uh,
Rujita, yes,
sir,
I can see your,
yes.
I can see your point. Yes, the answer is correct, and the
That
point is
formula I use, is it right, sir? Well, flow in meter cube per day into inlet BOD divided by volume of tank and MLSS in milligram per liter.
is
I use directly this formula and I calculate the FMS. Is it right
yes,
now?
yes, right.
Yeah, during examination, I can put this equation to solve the problem. Is it right?
Yes.
Okay.
We tell you, you can see like both the governments like. Yeah. So this was our question. You can check uh, whatever I have written. And this similar to you, like yes, you meter per TED in let beauty find and then right, absolutely right. So you don't have any issue with your formula. Two versions are there. One is this one which you have used, and another is this one. Nothing, just we converted this Q by V as S at T. So sorry, H at T. So that's it. No other problem is there. So this was my flow rate, right? Q equals to 500 meter cube per hour, and then influent BOD was S naught, that was 150 mg per liter. It was given. Effluent going out from the tank was 10 mg per liter. Going as effluent as 10 mg per liter, it was carrying that much of BOD. Then H at T was given as 8 hours or 1 by 3 day, and then mean cell residence time, that is C, that is 240 hours, or you can convert it into days, 10 days, and MLSS, that is X, is 2000 mg per liter. So I think this much data is clear for you. Then this is my FIM ratio. This is nothing but conceptually, if you see, that is total applied substrate or total applied BOD divided by total microbial mass. Whatever BOD or substrate or the food is coming, divided by total microbial mass. So here we are writing as Q multiplied by whatever the flow is coming into the system, into this tank, Q, that is Q. Whatever the inlet BOD is coming as S naught, that's Q multiplied by S naught. Now this is the volume V, and whatever MLSS is there, that is X. So this is nothing but this ratio, and you can convert this Q by V as theta. So you know how to convert this Q by V into theta. So this is in the two forms I have written. One is this form, another is this form. So this is 500 multiplied by 150, 500 meter cube, that was volume, and sorry, that was the flow rate. And then the influent BOD S naught was 150, and that is divided by your V. What is V here? V was given as 400, 4,000. You can check from here. It was not there. I missed it. So it is 4,000 meter cube and multiplied by 2,000. That is MLSS. We are multiplying with 24 to make it into hours. Right? Sorry, the conversion was, yes, it was asked per day, right? Yes. To make the conversion, we are multiplying with 24. And then again, we have, because it was in hour, right? So we are multiplying 24 to get per day calculation. Again, you can convert these hours into day, 1 by 3 day. And here, similarly, I can write S naught was 150 mg per liter. Then 2000 was my X or MLSS and multiplied with 1 by 3. That is my H at T. So you can also write in terms of H at T also. The same answer you will get 0.225. So the next question is the mass of the solids wasted from the system is, you have to calculate. This is also easy question. No need to think big. I can go back to the data slide. This one is your data, and this is the mass of solids wasted from the system.
Sir, so the question?
Uh, can't you see the question? Like, is there any problem? This was the data slide.
Yes, right, right.
Uh, Maybe there is some problem with this figure. Please don't like go by this figure totally. From the question, you can grasp what is the real scenario. So I will not suggest you to particularly go through this figure. Otherwise, it will be confusing.
Sir, answer 800 kg per day is,
Oh,
I
yeah,
find.
800. Okay, we'll check if there is any error. We'll try to correct. So the yes, answer is 800, right?
Yes, I find
Zero.
800.
Okay, so thank you so much. So the option D is 800, and the 800 is the correct answer.
Sir, I use formula. Just I
Hmm.
want to discuss with you. Um, MLS is in milligram into volume of tank divided by 1000 into slash quantity in kg per day. SRT is equal to I use this formula and
Okay.
I find out the answer of X, that is base to something.
Yes, yes. I think that whatever you're saying is right. Like that's how we will try to solve. Your formula is correct. So for others, I'm just saying you can also like tally. I may have written in a different way, but it's the same concept. So mean cell residence time, which we use theta c as Vx multiplied by wasted. Why I told everyone that don't go by this figure, because there is something recycle written, but in this question there is no mention of the recycle thing. So it's better we will assume that everything is going to be wasted, this one and as well as this one. We are thinking this as a collective summation of these two. So you don't need to think about the q minus qw multiplied by xv plus qw multiplied by xr, which I told you in the beginning. At the beginning, I told you there was a similar question where I used this kind of formula. But here you don't need to consider all those factors because it's very simple. Because everything is we are considering is getting wasted because there is no mention of any recycle thing. So whatever is inside this chamber, whatever is inside this tank, that is V multiplied by X and divided by whatever is getting wasted. I can write as the flow rate is QU and XU is the concentration of the biomass which is getting out from this tank, right? So this is basically QU multiplied by XU. XU is the concentration of the biomass and QU is the flow rate, and this is V is the volume of this radiation tank, and X is the MLSS concentration. So this is the mean cell residence time. This is the concept behind this theta c. So I can write this as the solid wasted. So solid wasted per day can be written as XU multiplied by QU, XU multiplied by this one XU and this one QU. That much quantity of the solid is getting wasted. That is nothing but Vx divided by theta c. Just you have to put the values. The V was 4,000 and then I multiplied with 1000 to make it, it was I think meter cube something, right? Yes, it was in meter cube. So you can convert this into liter. You may try any kind of conversion, but all the units should be in the same unit, like liter, liter, meter cube, meter cube. So that thing you have to take care of. And then there is 2000. 2000 is my MLSS concentration, mg per liter, I guess. And then this is theta c was written as 10, right? So I'm getting 800 kg solid per day. We'll move to the next question. Theoretical conceptual question about equalization tank. Quickly type your answer.
Answer C. Option is C.
Uh, okay. So you have given us C, right? Fine. But there are multiple correct statements, so be careful about that. Anything else you want to say apart from C?
Answer A and B.
Okay, thank you,
Boiler.
Abdul. You were saying A and B, and Ruchita is saying C. Okay, finally we'll go A, B, C are the correct answers because you can see that biological treatment, if we are not using this equalization tank, I told this thing earlier also, there will be some shock loading. So we should minimize or at least minimize or eliminate this offloading to these microorganisms. So this is the correct answer. Then slow liquidation is an attractive option. Suppose you have a treatment plant in your city, but you want to upgrade that, then you can add a flow equalization tank. If the flow pattern is changing and you need to upgrade that, you don't want to make another treatment plant. So for upgradation, this is very good attractive option. And then see inhibiting the substances, it can be diluted because more water is coming and pH can be stabilized. So the next question is choose the correct results for of keeping SRT too short.
What is sir XC? XC?
That is the effluent biomass concentration.
Pardon?
Effluent biomass concentration.
Okay, MLS.
Sorry.
MLS, mixed
No,
liquid suspension.
MLSS is inside. We always refer this MLSS, which is inside the aeration tank. But whatever the biomass concentration is going out, that is XC. I already told this in the previous question. Maybe I'll go back there. No problem.
Okay, okay.
So I'll go for the solution. So the correct one is 1, 2, and 3. Very cheap. I got your answer. 1, 2, and 3. No, 1, 2, and 3 is the correct answer, not A. This is 1, 2, and 3. That is C. Why? Because I already told, I guess, here. Let me check this one. So this is my XC. What is XC? This is my tank. This is the effluent water, treated water. Maybe there is one secondary sedimentation tank. I'm not considering that now, just writing like that. So suppose Q was my flow, initial flow. Now how much flow is going out? Q minus QW. That much is going out. This is the flow rate. What is the concentration of the biomass here? That is Xc. What is the concentration of biomass inside this tank? This is X. This is MLSS. We generally refer to this MLSS. And this is the effluent biomass concentration. What is going out? It is going to the river. Suppose it is we are disposing this into the river. So this is the flow rate and this is the biomass concentration. It is going to the river. And then suppose some part of the biomass is going to be wasted. That is QW. Or it can be recycled. That's why we are writing XR, or you can write as XW also. You can write as XW. So this is the highest biomass concentration we are having. We may go for this recycling, or we may go for dryer and other systems are there. So this is going to be wasted. That's why we are saying this is wasted. So this is X. So what is happening if you are keeping SRT very low? Then what will happen? This cannot be high, right? Because what will happen? This biomass will not be able to get consolidated at the bottom. So it is like floating kind of thing, you can say. It is not precipitated or it is not reached at the bottom. So if it is rich at the bottom, then we can take it to the secondary sedimentation tank and we can go for the secondary sedimentation. But if it is in the floating condition, then it is very difficult to make them settle. So there will be some settling issue. First of all, there will be the sludge bulking because the sludge will be in a bulk mode. It is not properly settled or it's not properly thickened. Or in other terms, you can say the density is very low. The density should be high to get it settled, right? So this is the first thing. It will be in a bulking mode. Then the poor settling, same thing is repeated. So if it is in a bulking mode, then it will be not be able to settle properly. Then the dispersed sludge, same thing we are saying. And no, not a low XC, because the whatever water is going out, it will take this floating kind of biomass. So if the biomass is properly settled, then we can take it out from the effluent water. So otherwise, it will be in a dissolved form, or better to say, it will be in a floating form. We are taking out this biomass with our effluent water. We are disposing that much of high content of biomass into river or any other water bodies. So this is not a good approach, right, to keeping SRT too short. This is a difficult situation. Now, what is total kg dull nitrogen TKN concentration? Again, conceptual question or theoretical question.
C option.
Okay, thank you, Vijita. We'll go for the solution. So the correct option is C. TKN equals to organic nitrogen plus free ammonia. That's what TKN means. Next, again, conceptual question about this graph. I think all of you are aware of this graph, both curve for bacteria or any microorganism. So you have to match stationary phase, lag phase, and then the exponential growth phase, death phase. Then we'll go for the solution. So C is the correct answer. Here you can see that first one will be the lag phase, then the second one will be the exponential growth phase, then your stationary phase we are getting, and then the death phase. So how these things are happening? Suppose I have some colony of some amount of microorganisms. I put them in a aeration tank or whatever your beaker or whatever culture media with food for them. But initially, it will take some time for them to adjust. This is the time axis, t axis. This is the log of the bacteria, number of bacteria. So basically, in this portion, they will try to acclimatize with the environment. They will try to be comfortable with the pH range, the temperature, other physical and chemical factors. So the initial growth will be not much. So this is very low. There is not much growth. They are trying to be acquainted with the environment, new environment. It will take time. Then there will be exponential growth. You can see this is the exponential growth. After some time, there will be after this exponential growth or during this exponential growth also, the death of the bacterial cells are going on. But at this point, the death and the birth of the bacterial cell will be same. The generation of the bacterial cell and also the death of the bacterial cell will be the same. So we will reach this saturation zone that is called as the stationary phase, and then at the end we are getting the death phase where the death rate is higher than the growth rate, or the death rate is higher than the generation rate or the birth rate, whatever you can say. So we are getting this declination of the graph. So the next question is, we will skip this question. Oh, no, no, we'll skip this question. Sorry, I thought a different question. So this is from the manufacturer of aviation device reports that oxygen transfer rate of the device. You can see if you purchase any oxygen transfer device, something is written on that instrument box, and we obtain through the laboratory test something standard conditions. So what are the standard conditions? This is theoretical question only, not even conceptual question.
Sir, what is the meaning of your aeration device? That's the manufacture of an aeration device.
Yes, there are some kind of aeration device. Have you seen or have you gone through the lecture? Like, was there anything in activated sludge process? If we need to aerate, there are some pump kind of thing which, like, in case of water, what happens if there is some kind of flow rate and it transfers oxygen. In case of this aeration device, it transfers oxygen to the aeration tank. That oxygen can be used by the bacteria.
Is it
By the,
diffuser? Is it diffuser?
yes, yes, that another name you can say that.
Okay.
So this is not a numerical question, just information based question. That's why I said theoretical, nothing conceptual.
Okay.
So there is a standard protocol for measuring the oxygen transfer rate, and when some company is preparing the aeration device, they will test in a particular condition because they cannot test in a different conditions, and we can change and we can apply in different conditions based on our situation. But they there is some universal standard conditions available for the manufacturer. So here, that is the question: what is the standard condition?
This is option D.
Okay.
Yeah, it is option D, wastewater at zero dissolved oxygen.
Okay.
25 degree, that is ambient temperature. Normally it is coming in the lab, 25 degree centigrade. Then I think it is D, wastewater, zero dissolved oxygen.
Okay, thank you both of you for giving the answer. So we'll check. So the answer is C, not D, that I was thinking that you were saying about the wastewater. But when the manufacturer will prepare, I gave the hint already. When the manufacturer will prepare, he or she will try to be standardize his device. So tap water can be standardized. I'm not saying that tap water everywhere should be standardized, but to some extent we can go all the parameters should be in a particular range. But in case of wastewater, it's very difficult. Like in my city, the wastewater, the conditions, the parameters might be different than your city. Even throughout the globe, it is different. So it is very tough for wastewater to standardize. But for tap water, we can go to some extent. There might be some range, there might be variation from your city to my city, but we can go with some range, right? Other thing is 20 degrees centigrade and 760 mmHg. That is the pressure. Now the select the suspended type of, yeah, this is a very easy question. Select the suspended type of treatments from among the different treatment systems. Okay, Ruchita, I got your answer. A, right.
But
Abdul, yes, A. You are also saying A, right? So there are multiple answers. I hope like you have gone through this lecture. I'm not sure like is it going beyond or not. So the activated glass faucet is right, but there are multiple options. Like trickling filter is not, absolutely not. But in case of stabilization pond, what we used to do earlier days, there were stabilization pond. Then people developed the activated sludge system. So initially, if you go back to the history, you will find the stabilization pond was there, and then also this aerated lagoon. But this trickling filter rotating biological filter is different. Rotating biological difference, there is some device like that and it will rotate. If this is suppose the water is coming this way and what is going this way, and these are the some drums kind of things are there. So I hope you know about this rotating drum thing. So it will rotate in this way. It is advanced version of this trickling filter. Trickling filter is nothing but some kind of stones are there and water is percolating through that through those stones. That is the trickling filter, and that is attached growth system. So this is attached growth system, not suspended. But this is attached growth system, right? And this is also attached growth system. There's some modified version of this trickling filter. So A, B, and A, C, and D are the correct.
So what is modified word of tickling filter? Atos? I don't understand.
So I'm not saying this one is attached. You know what is attached growth system? I hope you know what is attached growth system, right? What is the
Can you
difference
write
between?
this word? Can you write down this word in message word? I don't listen
I am saying
understand.
attached growth system. Attached growth
Attached.
system.
Okay, attached good. Tickling
Yes,
filter is attached good. मतलब there is some biomass media you like MBBR media.
yes, right, right. No, no, no. Not not I am talking about this NBR media. I'm talking about different thing. Do you know what is trickling filter?
About the process of this, sir.
Hello.
More. मतलब I have listened the word. I have listened about this, but don't know the process. How it is.
Okay,
How
okay,
it
okay,
is
okay,
work.
okay. No problem, no okay, problem. I am telling you in a very short manner, but I will recommend everyone to go through your lectures or note or any book. Then you will find. So suppose these kind of things are there. This is nothing but a trickling filter. What will happen that wastewater will come from this direction and it may go from this direction. So the water will percolate. These are the stones. I think you can see these are the stones. I have many boulder kind of stones here stacked in a particular position or in a container. There, this is the wall. You can say this is the wall. Water is coming from this way and going down from this way, or we can collect from this way also, no problem. So what is happening? Suppose this is a stone. Wastewater is coming with the BOD or the organic matters, whatever is present inside the water, and there are bacteria which are eating and growing, right? Which are eating this water and growing. So after some time, what will happen? This thickness will go. Suppose this is my stone, and this is my bacterial cell growth. So they are accumulating. They are getting their food from the water, all the organic matter, and they are growing. After some days, they are growing like this and growing like this. So after certain amount of growth, they will slack off from the stone because the gravity will be higher than to hold them. And there will be other issues also because the whatever is the inner portion which is actually attaching with this stone, they will not get proper oxygen. They will not get also proper food. It will be very hard to penetrate this much way to get the food for them. So it is very hard for them to get the food and even the oxygen. So what will happen? They will be weak, they will die, and it will eventually slag off from this stone. So we can collect the water from the bottom as well as the solid biomass from the bottom. Both can be separated from the bottom. This is the example of attached growth system because here all the biological cells or the bacterial cells are attached to the stone or attached to any media. So this is one example is a trickling filter, and another example is this rotating biological filter. Here what I said, instead of this thing, this big stones, we are providing some big drums and it is rotating continuously. So what is happening here, you can see, I said this is some kind of modification we have done. Uh, Suppose this part was under the water, wastewater. This is wastewater coming and wastewater is going in this way. So this portion of the drum was immersed in the wastewater, and after some time it is going up, right? This part will going up because this drum is rotating like that. So sometimes it will be down and sometimes it will be at the top, and again it will come down and this portion will go at the top. So what will happen, they will continuously get the oxygen, and due to this movement they will also slag off from this drum, from the surface of this drum, and they will be at the bottom. They will settle at the bottom of this tank. So we can uh, remove them, and also we can get the supernatant liquid. I hope now this is clear. And this is again regarding primary sedimentation tank, some basic question. I'll go for the solution because to solve many questions. So and A and C is the correct answer. The primary region variables are well loading rate, detention time, and depth, and you have to take care of the short circuiting. Otherwise, if the velocity is very high, then it can take away many settling items, objects which could be settled down. But if the speed is very high, then we take away with this. And you need to take care of the flow distribution. If it is not properly distributed, then there might be some the settling will not be good. It will hinder the settling. Again, this one is a theoretical question regarding settling process in the secondary settling tank. Which of the following is mainly involved, or you can say are mainly involved in the settling process in secondary settling tank? Okay, Ruchita B, you are saying hindered settling, right? Okay, fine, we'll go. So there will be another one, not only one. One is hindered settling, another is completion settling. So hindered settling we can say as a blanket settling, two kind of thing is going on in the secondary sedimentation tank. One is the it is coming out as hindered settling with respect to other particles like a blanket, And at the bottom also, whatever is already settled, they are also compressing it and water is going out, right? The net weight is coming down, and due to this compression, this layer is getting compressed layer by layer. So suppose at the bottom it was already that much, then again after some time it is going to this height, and then it is going to be reduced this height and water is coming out from this layer. So both this compression settling and the settling, right? Both A and B. Again, numerical question, same as the previous one. You already solved, so I hope you will try to solve this. Same thing, same formula, same repeated question. Try to solve this quickly, as you already have done this. Just to recap, I could put this question. Okay, Ruchita, thank you. I got your answer. Abdul, are you trying, or otherwise we'll go for the solution? 5.32 hours. Okay, hence 5.32 hours is the correct answer. Here I am dividing 665 divided by 3. We are not converting anything, because you can check why we are not converting. That is, you need to do by yourself, like how this conversion is going on, and there is no need actually to convert like anything multiplied by 1000 or anything else, because everything will be cancelled out in such a way. So this much days, and if you convert into hours, I'm getting 5.32 hours, right? So again, the solid retention time, SRT, you have to calculate. Please calculate this quickly. Again, the repeated question. You need to calculate SRT.
Sir, please show the question.
Okay, sure. Solid retention time. In days, you can calculate.
Sir, please show the details of the
Oh,
question. And then, yeah.
okay. You are saying 5.03 is that. 03. Yes, you are correct. So again, same thing, same formula I am using. Theta c equals to v multiplied by x, xt, whatever you can write, and then xw multiplied by xr, whatever was going wasted or recycled, and then Q minus QW multiplied by XC. I told what is XC already. I told what is XR, what is QW, and everything. So you just need to put the values. V was here 665 meter cube. Then X30 was 2,500 mg per liter. I guess that was MLSS. Then I'm multiplying with 50. Then this quantity of sludge getting wasted and multiplied with my XC. How much water is that? 6,600 mg per liter. So if you just put the values, you can convert the units. If you don't need to, you don't need to convert the units, because if everything is in meter cube or meter cube is getting cancelled, or your liter is getting cancelled, then it's fine. Just check the units and you will get 5.038 days. Right? So the next question is activated sludge is this very easy question.
Answer A and C.
Abdul, thank you. A and D, you are
C.
saying. C, okay. And Ruchita is saying A. Right. So here only one answer will be correct. That answer is C only, because that sludge in the secondary tank after the irrigation can reach in microbial mass. That is our activated sludge. The sludge is activated. It is containing microbial mass, as well as it is coming from this secondary tank after the irrigation. And that can be recycled. That's why we are saying that's activated, not the only the sludge, because sludge might be the dye biomass cell, but here we can recycle it into the irrigation tank and we can use them to eat the food. What is our food? That is nothing but the organic matter present in the water. So we can use them to eat those organic matter, and organic matter will be removed eventually from the effluent water. That is our target, right? So the next question is, the flow sheet of the liquid stream of the sewage treatment scheme consists of. You just have to tell the correct sequence. Sequence is very easy, right? Only the correct sequence you need to tell in terms of sewage treatment plant. Okay, I got answer from Ujita, that is C. So you are saying screen chamber, then grid chamber, then your primary settling tank, then biological treatment and secondary settling treatment. Yes, C is the correct answer. So no need to wait more in this question. Next question again regarding F by M ratio. Again repeated question to reconnect you your ideas. Okay. Please try to calculate this quickly, because already done. You have the formula, you know how to calculate.
Is it point four 416?
Okay, Abdul, thank you. I will check point 416.
Okay, okay, sir.
Ah, thank you. Okay, Ruchita is also saying 0.416. We'll go for the solution. Yes, right. Congratulations, Abdul. Congratulations, Ruchita. Right answer. So this is A by M. Again, Q multiplied by S naught divided by V multiplied by X. I already told what is the full form, what is the meaning of this V, X, Q, and S naught. So I'm not repeating again. And here, Q, what was the flow rate? 10 mld, right? 10 we are writing, then we are writing 225, right? Huh? Yes, that was the influent concentration, 225 mg per liter of concentration. And then we'll go for the volume, how much volume it was, 2000 meter cube, and multiplied by MLSS. MLSS concentration was 2700 mg per liter. That is MLBSS or MLSS, whatever is given. I'm writing that. And you need to convert, if you need from meter cube to liter, liter or meter cube, ml to liter, that conversion you need to do. And if you do this conversion, if you calculate, you will get 0.416, right? That is our correct answer. Then again, theoretical question. Select the major nutrients required for biological treatment. Among these,
It is nitrogen and phosphorus.
thank you, Abdul. Nitrogen and phosphorus. Yes, Ruchita is also saying same. Correct answer, nitrogen and phosphorus. And this question, efficiency of a sedimentation tank does not depend upon. I think this one is the same type of question. Okay, Ruchita is saying depth of the tank, right?
That is the depth of tank. It is
Ah,
not a criteria for that.
thank you,
Depth of,
Abdul. Yes, depth of the tank, right? I already discussed this question, I think, in the last session. Right? So, thank you everyone for joining today's session. I hope you enjoyed, learned many things. So, we'll meet in the next session on next Tuesday. Right? Thank you for joining.
Sir, can I discuss something else regarding last session?
Okay, yeah, tell
Just,
me.
I need 2 minutes.
Uh,
Last you, we solved the question regarding settling velocity.
yes, yes,
Uh, Settling velocity. There we solve the using the trial and error method.
yeah.
First, we use assume laminar flow
Mm-hmm.
during calculation.
Mm-hmm.
Second, we check the Reynolds number.
Yes,
Third option is
we were checking the Reynolds number multiple
yes,
times.
yes.
Yes, yes,
Huh. Third option we use CD is equal to 24 by RE plus 3 by RE the power zero point 0.5 plus 0.34. What
yes.
is the CD? What is CD there?
Okay, that is the coefficient of drag. So if
Coefficient of drag.
yes, yes,
Of the drag. Okay. And fourth, we use the VS settling velocity square is equal to 4 by 3 something formula.
yes, yes,
And fifth option, we repeating the option 2, 3, and 4.
yes, 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 yes,
Sir, I don't understand why we are repeating this option because we solve the question assignment question number 2. There is given find the terminal velocity of a spherical particle with a diameter of 0.25 mm settling through water.
yes.
Refer data given as below. So I solved this equation, but I'm not sure it is right or wrong.
Okay,
I saw three options there.
Okay.
but I
Yes.
have confusion. Is it
Okay.
right or
Fine.
not? What and next I have to do
Okay.
something.
Fine. Fine. So yeah, I think this one is visible. Just let me check.
Sir,
Okay. Yes.
someone
I think now it will be visible. Just wait. The previous PPT, I think it will.
assignment for question number 2.
This was the last question which you were asking. Like it was repeating many times, right? This is visible for you.
Yes, you sure,
Ah,
huh? I saw
yes.
this question.
Yes. You were asking about this question, why we are repeating this,
Uh-huh.
right?
Yes,
Yes.
yes, right, sir, right, right.
Right. So what
Uh,
happened here? See, it was
yes,
given is that nothing was mentioned, whether it's laminar flow or the turbulent flow or the transitional flow, nothing was mentioned, right? So first,
yeah,
we what we have done, we suppose we assume this is a laminar flow. We don't know whether it's laminar flow or not. So
okay,
so we calculated the velocity from here, and then we check the Reynolds number. So when we put this
okay,
velocity, this is the velocity I got from the considering laminar flow. I'm getting this. You put this velocity here, 0.225 here, and
yes,
then you can put all the values here, right? And I'm getting yes 100 and how much 112.2 sorry 2.5, right? That much. So it is
yes.
crossing 100. So I can assume that this is a transitional flow, right? Then we are
It
using this.
indicates transition and flow.
Yeah.
Okay. What is the range of Reynolds number? Like
Uh, if
any?
if if it is crossing this 100 like 100, then it will go for transition. It will cross the 1,000. It will go for this turbulent flow. So mostly in most cases we will find this is transitional or laminar. So if it is within 100, then in our case it is a laminar. So it's simple. Like the first question you are talking, like question number two, it was written as laminar flow. Like you go to question number two, I guess. It was already mentioned there. So that's why we didn't do this. Question number two or some question was there. Yeah, I saw it.
Yeah, yeah. There is part
Ah,
six. I was
it
trying
was,
to
it was,
find.
yes, right. It was fine. That was written as laminar flow, but this is not the easy question. If it is not mentioned in the question, you can try. You can
Okay,
check. If it is mentioned in the question, laminar flow, fine. Don't need to go all those steps, right? Just leave it there.
okay.
Yeah. So it was not mentioned. That's why we are doing this check. We are checking this Reynolds number. I'm getting 112.5, right?
Yes.
And then what happens is we are doing this. There are formulas. I think that's in the note. I'm not sure whether it's in lecture. Please go through the lecture. If it's not there, I'll give you some PDF kind of thing. So it will be easier for you to take care. So then we will check this coefficient of drag. That's why I'm saying if you don't find that in the lecture, then I will provide you. No problem. The next session or before the next session, I can attach with this PPT also. So this is CD. This is nothing but the coefficient of drag. This is the formula here. So
Okay.
if this is not the laminar flow, that's why we need to check this. Now CD, I got this Reynolds number, right? That is
Yes.
112.5. So put this value here in this equation in the place of RE and check what is how much CD is I'm getting. That is 0.836. Okay. Then we have to use this original formula. This formula
Okay.
was for laminar flow. I considered everything as laminar flow. That's why I get this formula. There is a derivation. How from this formula? From this is the original formula. From this formula only, I am getting this formula. So there is a derivation. If you don't find this in the notes or in the lecture, then I will give you. Just let me know. I think this is available in the lecture. Just go through it. This is the mother formula. From this formula, if you adjust this for laminar flow, you will get this formula. So here I need to consider CD. Here I'm not considering CD and other factors, but here I need to consider the CD. So I put the CD value from here, that is 0.836. I put the G value, you know what is G, 9.81, you know what is the D diameter, you know what is the G, what is 1, 1 is 1, sorry. So you can calculate what is the value of Vs. I'm getting Vs as 0.113 meter per second, right? Then what I
Yes.
will do, I will again repeat the process. this I got as for transitional flow, but I need to check whether now it is transitional flow or it is crossed or there is some changes, right?
Yes.
So I got this RE again here. Again, I will use this CD value to calculate this CD value, right? You can repeat this process CD value. Now you see one thing you may need to measure. Like that is the main thing here. See what I am getting. This is at 0.09. Now forget RE. Now forget CD. Everything. Considered here that PS value is 0.0965 meter per second, right? And here I
Yes.
considered initially that is 0.1133 meter per second. Right. So these two are not closely matching. So we need to continue. Maybe you need to continue not only this step. If you need to continue for 5 or 6 or 7 steps, it may go. But in examination, you will not find such tough question. But for saying, like I am saying, that it may happen. You may have to go for that much. So you again, I am putting this value. Again, I am
Yes. Yes.
calculating everything. I am trying to get this as close as possible. Now this value is closely connected, like almost 0.09 is almost 0.09. So we can say this
Yes.
is we can as a 0.09 or 0.962 is fine. So until and unless you are getting two values as same, I am just repeating this step. That is the main thing. Once I am checking, after that I am just trying to make these two closer, as close as possible. That is my trial and error. Like here, now forget about RE and CD and all. Now I am trying to get it. So I will provide you. It will be better if I provide you the derivation and all. So it will be easier for you to check. I think that.
Okay.
So I
Thank
will
you.
try to upload this and the new PPT, the number four or the third PPT. I will modify the third PPT and I may add some additional slides.
Okay. Okay.
Ah,
Thank you.
thank you.
Thank you so